The question is whether we'll rise to the occasion or watch the opportunity drift past like so many others, lost to circumstance and hesitation. But even if we miss this chance to fly through the tail, 3i Atlas has already revealed secrets that challenge everything we thought we understood about how comets behave. And some of these secrets suggest this object is even stranger than we initially realized. Here's something that should be impossible. When astronomers discovered 3i Atlas on July 1st, 2025, the comet already displayed clear signs of activity. A visible coma, that fuzzy cloud of gas and dust surrounding the nucleus, and even a small tail. This made sense. Comets activate when solar radiation heats their surface, causing ices to sublimate into space. By July, 3i Atlas was close enough to the Sun for this process to begin. Everything appeared normal, textbook behavior for a newly discovered comet. But then scientists did what they always do with new discoveries. They checked archival data. They searched through images captured by other telescopes that might have accidentally photographed this region of space before the official discovery, and they found something that shouldn't exist. The TESS Space Telescope, designed primarily to hunt for exoplanets around distant stars, had been photographing the area where 3i Atlas traveled throughout the entire month of May 2025. TESS operates by staring at large sections of the sky, taking an image every 200 seconds, watching for the telltale dimming of stars as planets pass in front of them. This continuous monitoring creates massive archives of data, and buried in that data were nearly 9,000 images of 3i Atlas, captured when the comet was still far beyond Jupiter's orbit, roughly 900 million kilometers from the Sun. At that distance, in the cold outer reaches of the solar system, 3i Atlas should have been waking up. Solar heat, though weak, should have been enough to start sublimating the frozen carbon dioxide on its surface, creating a detectable coma. This is what comets do. This is what they've always done. The distance was right, the conditions were perfect, and later observations confirmed the comet was indeed active during this period because its brightness was steadily increasing. But when researchers from the University of Maryland analyzed those May images, they were confronted with something deeply strange. The comet had no visible coma. None whatsoever. To confirm this impossible observation, they compared 3i Atlas's brightness profile with those of ordinary asteroids, dead rocks that show no activity at all. Brightness profiles reveal how light spreads from an object's center to its edges. An asteroid creates a sharp profile because it's just reflecting sunlight from a solid surface. A comet creates a diffuse, blurred profile because the coma scatters light in all directions. The difference is unmistakable. 3i Atlas's profile matched the asteroid's perfectly. Sharp, clean, no fuzzy edges, no signs of any surrounding gas or dust. It looked, by every measurable parameter, like a completely inert object, a dead rock tumbling through space. But it wasn't dead. The brightness data told a different story. Starting in mid-May, the comet's overall luminosity began increasing gradually. This is the signature of cometary activity, the unmistakable sign that gas and dust are erupting from the surface. The object was actively outgassing, releasing material into space, and yet somehow remained completely invisible as an active comet. This is the paradox. The comet was behaving like it was active, but looked like it was dead. How do you explain an object that's simultaneously erupting and appearing dormant? The researchers developed a theory that sounds almost like the comet was hiding from us deliberately. They proposed that 3i Atlas did have a coma during May, but it remained invisible to TESS for two interconnected reasons. First, the gas and dust might have been escaping so slowly that they never formed a wide, detectable cloud. Instead of the violent eruption we typically associate with comets, imagine a gentle seepage, material oozing from the surface at speeds barely above a whisper. This could be related to the comet's unusual composition or its exceptionally low temperature, even at that distance from the Sun. The sublimation was happening, but in such a subdued manner that the particles stayed close to the nucleus, forming a dense cocoon that didn't spread far enough to create the typical fuzzy appearance. Second, and this is where it gets really interesting, the size measurements reveal something suspicious. Based on TESS observations, scientists calculated the object's diameter at roughly 6 kilometers, but when the Hubble Space Telescope, with its far superior resolution, measured the actual nucleus, it found something much smaller, between 2.8 and 4.4 kilometers in diameter. Where did those extra kilometers go? The answer is unsettling. TESS wasn't seeing a naked nucleus. It was seeing the nucleus wearing a mask. A hidden coma so compact and dense that it appeared solid. Imagine looking at someone through frosted glass, so thick you can't tell where the person ends, and the glass begins. The coma was there all along, wrapped so tightly around the nucleus that the two became indistinguishable. A cosmic disguise. The comet was hiding in plain sight. This is what they're calling the hidden coma phenomenon. An invisible shroud of gas and dust that clung to the comet's surface like a second skin, detectable only through its effect on the apparent size of the object. It's a cosmic illusion, a trick of observation and physics that caused the comet to appear as something it wasn't. The implications extend far beyond this single object. How many other comets have we misidentified because their comas were too compact to detect? How many asteroids in our catalogs are actually dormant or weakly active comets hiding in plain sight? The techniques we've relied on for decades to distinguish between asteroids and comets might be missing an entire class of objects that fall somewhere in between. 3i Atlas is teaching us that the universe is full of deceptions. Even our most powerful instruments can be fooled. Even the fundamental categories we use to classify celestial objects might be more fluid and ambiguous than we realized. This comet spent weeks traveling through TESS's field of view, captured in thousands of images, and yet it concealed its true nature, through physics we didn't fully appreciate until now. The hidden coma revelation changes how we understand the comet's early behavior. It means 3i Atlas was active much earlier than we thought, potentially beginning its sublimation when it was even farther from the Sun, in the frozen darkness beyond Jupiter's orbit. It means the processes governing its outgassing are fundamentally different from typical comets, operating on different timescales with different physical mechanisms. And it raises an unsettling question. If the comet could hide its activity from us when it was distant and cold, what else might it be hiding now that it's closer and warmer? What other phenomena might be occurring around and within this object that we simply don't have the tools or knowledge to detect? There's something almost deliberate about how 3i Atlas has revealed itself to us. First appearing as a normal comet, then showing that extreme carbon dioxide composition that defies our models, then demonstrating water production at impossible distances, and now we discover it was concealing its activity all along, presenting different faces depending on how and when we looked at it. Some might say this is just the nature of scientific discovery, that new observations always complicate our understanding. But there's a pattern here that's hard to ignore. Every time we think we understand this object, every time we fit it into our existing frameworks, it shows us something new that doesn't quite fit. It's as if the comet is challenging us, testing the limits of our instruments and theories, revealing the gaps in our knowledge, one mystery at a time. The ghost comet, as some researchers are starting to call it, isn't finished surprising us. Because in addition to its hidden coma and all its other anomalies, astronomers have detected something even more bizarre, something that shouldn't exist according to basic cometary physics. But we'll get to that in a moment. First, we need to talk about what might happen if neither Europa Clipper nor Hera can study the tail, because there's still hope for capturing this interstellar visitor's secrets before it vanishes forever. Even if the spacecraft encounters fall through, the European Space Agency's JUICE mission, currently on its way to Jupiter's moons, will be observing 3I Atlas throughout November. Scheduled observations will occur on November 2nd and again on November 25th, capturing the comet as it begins its long retreat back into interstellar space. JUICE won't fly through the tail, won't sample it directly, but its instruments can still study the comet from a distance, gathering spectroscopic data and tracking how its activity changes as it moves away from the sun's warming influence. It's not the same as direct sampling. It's like comparing a photograph to actually being there. But in space exploration, you take what you can get. Sometimes a distant observation is all that stands between understanding and ignorance. Now let's talk about what the Keck 2 telescope in Hawaii has been seeing, because this is where 3I Atlas stops being unusual and becomes genuinely disturbing. The spectroscopic data shows something that shouldn't exist: pure nickel vapor, streaming off the comet's surface in significant quantities. And here's the problem: there's no iron. Let me be clear about what this means. Nickel and iron are cosmic twins, forged together in dying stars, bound together in planetary cores, inseparable in every meteorite, every asteroid, every natural object we've ever studied. Finding one without the other is like finding a shadow without an object casting it. It violates one of the most fundamental patterns in cosmic chemistry. Except here it is. Pure nickel, clean, refined. The spectral signature is unmistakable. And here's what should make you pause. That chemical fingerprint, that ratio of nickel without iron, looks exactly like industrial nickel refining on Earth. The MOND process, a human invention, chemistry that happens in factories, not in frozen comets drifting through the void. On Earth, we produce pure nickel through a process called the MOND process, which involves nickel carbonyl, a compound where nickel binds with carbon monoxide. It's a toxic, volatile substance used in metallurgy and industrial applications. It requires specific temperature and pressure conditions. It requires chemistry that happens in factories, not in the frozen vacuum of space. And yet, the researchers from the University of Hawaii suggest that something similar might be occurring inside or on the surface of 3I Atlas. The comet's extreme carbon dioxide and carbon monoxide content, combined with whatever exotic processes are happening in its interior, might be creating conditions where nickel carbonyl forms naturally. The compound would then sublime into space, releasing pure nickel vapor while leaving iron locked in the comet's rocky matrix. This is where the scientific explanation starts to feel inadequate. The researchers suggest that natural carbonyl chemistry might be occurring inside the comet, that the extreme carbon content combined with unknown internal processes might coincidentally produce the same refined nickel signature that human industry creates on purpose. Maybe. Chemistry follows rules, not intuition. If the conditions align, the reactions occur. But here's what keeps astronomers awake at night. We're being asked to believe that nature, through pure accident, recreated a human industrial process inside an object from another star system, an object that also hides its coma, that produces water where it shouldn't, that develops impossible antitails, that reveals its mysteries in perfect sequence as if following a script. One coincidence is interesting. Two is notable. But this many? At what point does coincidence become pattern? The nickel anomaly isn't the only chemical mystery. The comet's gas composition remains utterly bizarre. Roughly 87% carbon dioxide, 9% carbon monoxide, and barely any water vapor despite the earlier observations of water production at 3 astronomical units. The ratios don't make sense together. It's like the comet is multiple objects with different compositions occupying the same space, revealing different faces depending on which instruments observe it and when. Then there's the antitail. This is perhaps the most visually striking anomaly, though its implications are just as puzzling as the chemistry. Most comets have two tails. The dust tail curves gently along the comet's orbital path, following the trajectory like a cosmic contrail. The ion tail points straight away from the sun, pushed by solar wind and radiation pressure. But some comets, under specific geometric conditions, develop what's called an anti-tail, a spike or projection that appears to point toward the sun rather than away from it. Anti-tails aren't supernatural. They're an optical illusion created when Earth's viewing angle aligns with the comet's orbital plane, and we're seeing edge-on what's actually a fan or sheet of particles stretching perpendicular to the main tail. It's a matter of perspective. From our viewpoint, particles that are actually spreading outward appear to be pointing inward. Except 3I Atlas's anti-tail breaks the rules. It's too prominent, too persistent, too wrong. The Keck Observatory images show a spike pointing toward the sun like an accusing finger, bright and sustained, appearing again and again under different viewing conditions. This isn't a brief optical trick. This is a permanent feature. Imagine watching a river flow uphill. That's essentially what we're seeing. Material that should be flowing away from the sun is instead forming a structure that points back toward it. The explanations involve exotic particle physics, unusual size distributions, unexplained interaction mechanisms, or maybe the anti-tail is connected to whatever is producing that industrial nickel signature. Maybe there's a process occurring inside this object that we simply don't have a framework to understand yet. A process that doesn't fit our models because it didn't originate in our type of stellar system. Let's step back and look at the full picture. An object from another star system, 10 billion years old. Carbon-rich composition, unlike anything in our neighborhood. It produces water at distances that should be impossible. It conceals its activity behind an invisible coma. It emits pure nickel vapor with an industrial signature. It develops an anti-tail that defies physics. It reveals each mystery in perfect sequence, one discovery at a time, as if on a schedule. Individually, each anomaly has a potential explanation. Scientists can construct hypotheses for each mystery in isolation. Maybe the water is ice grains. Maybe the coma is dense sublimation. Maybe the nickel is exotic chemistry. Maybe the anti-tail is particle physics. Maybe. But all of these anomalies in one object? The explanations start to feel forced. Like we're bending reality to fit our theories instead of bending our theories to fit reality. At what point does coincidence become too coincidental? At what point do we stop explaining and start wondering? This is not to say that 3I Atlas is artificial. That's not what the evidence suggests, and it's not what responsible scientists are claiming. But there's a middle ground between natural objects we fully understand and deliberately constructed artifacts. There's room for natural phenomena that emerge from conditions and processes we've never encountered. Exotic physics and chemistry that only occur in certain stellar environments or in objects of certain ages and compositions. 3I Atlas might be showing us what happens when material formed around a very different kind of star. Perhaps a carbon-rich giant that created chemical environments impossible in our solar system, travels through interstellar space for billions of years, accumulating cosmic ray damage and undergoing slow internal changes, and then suddenly gets exposed to our sun's radiation after eons of frozen dormancy. The combination of its exotic origin, its extreme age, and its sudden awakening might produce behaviors that seem impossible, simply because we've never seen this exact combination of factors before. Here's what makes this object particularly intriguing. If you were designing something to capture humanity's attention, to appear natural but remain mysterious, to prompt intensive study without providing easy answers, you might create something exactly like 3I Atlas. The timing is almost too perfect. It arrived during the precise decade when we can detect interstellar objects but still find them extraordinary. 50 years earlier, we'd have missed it completely. 50 years from now, such visitors might be routine, unremarkable. But right now, in 2025, we're at exactly the sweet spot of technological capability, advanced enough to detect and study it, not advanced enough to fully understand it. The trajectory is convenient too. Oumuamua raced through at breakneck speed, gone before we could really look. But 3I Atlas? It's moving slower, staying in optimal viewing range for months, providing ample time for observation. It's as if it's pacing itself, making sure we have every opportunity to notice its anomalies without revealing too much too quickly. And those anomalies unfold like a story with chapters: discovery, water mystery, chemical composition, ancient age, hidden coma, industrial nickel, impossible anti-tail. Each observation period brings exactly one new puzzle, never overwhelming, never boring, always just strange enough to demand attention. And the anomalies reveal themselves in sequence, like chapters in a story. First, we discover it's interstellar. Then we find the water production anomaly. Then the extreme CO2 ratio. Then the ancient age. Now the hidden coma, the nickel signature, the anti-tail. Each observation period brings something new, something that doesn't quite fit, something that demands explanation. Is this pattern meaningful? Or is it just how scientific discovery works, with each observation naturally revealing new complexities? The honest answer is, we don't know. We can't know. Our sample size is too small. We've only studied 3 interstellar objects in detail, and they've all been strange in different ways. We have no baseline for normal interstellar visitor behavior, because we don't have enough data yet. What we can say with certainty is that 3I Atlas represents a breakthrough in our ability to study material from beyond our solar system. Regardless of whether its anomalies indicate exotic natural processes or something more intriguing, the scientific value is immense. Every observation, every spectrum, every measurement adds to our understanding of what's possible in the universe. The next few weeks will be critical. Between now and early November, multiple opportunities exist to gather data that will shape our understanding of this object for decades. If Europa Clipper samples the ion tail, if JUICE captures detailed spectra during its November observations, if ground-based telescopes continue tracking the comet's evolution, we'll accumulate a dataset unlike anything we've obtained from previous interstellar visitors. The James Webb Space Telescope has also been monitoring 3I Atlas. Webb's infrared capabilities can penetrate dust and gas that visible light telescopes struggle with, revealing the comet's thermal properties and detecting molecules that remain invisible to other instruments. The combination of Webb's infrared data, Hubble's visible light imaging, ground-based spectroscopy from Keck and other observatories, and potential spacecraft encounters creates a multi-wavelength, multi-platform observation campaign that's unprecedented in scope. This is how modern astronomy works now. No single telescope, no single spacecraft can tell the complete story. We need optical and infrared and ultraviolet. We need spectroscopy and imaging and direct sampling. We need ground-based observatories and space telescopes and spacecraft instruments all working together, each filling gaps in what the others can detect. 3I Atlas is benefiting from this coordinated approach in ways that Oumuamua never did. When that first interstellar visitor passed through in 2017, we were caught off guard. The telescopes weren't ready, the observation protocols weren't established, and the object was gone before we could properly study it. Borisov in 2019 gave us more time, but it was still a scramble to organize observations and allocate resources. But with 3I Atlas, the astronomical community was prepared. Alert systems detected it early. Observation campaigns were organized quickly. Major telescopes dedicated time to studying it. Spacecraft missions evaluated whether they could contribute. This is what we've learned from the first 2 interstellar visitors: how to respond efficiently, how to coordinate internationally, how to maximize the scientific return from these rare opportunities. The data that's accumulating will keep scientists busy for years. The papers analyzing 3I Atlas's composition, behavior, and origin will continue appearing in journals long after the comet itself has faded from view. Graduate students will build dissertations on this data. New theories about comet formation and interstellar chemistry will emerge. Our models of planetary system diversity will be refined and expanded. But beyond the technical scientific value, there's something more profound happening here. These interstellar visitors are changing how we think about our place in the galaxy. They're making the cosmos feel more connected, more dynamic, more full of unexpected interactions. For billions of years, our solar system existed in relative isolation. Material formed here, stayed here, evolved here. We exchanged some debris with nearby stars during the sun's birth cluster days, but for most of our system's history, we were closed off. A separate island of matter spinning through space on our own trajectory. That isolation is ending. We now know that objects from other stars pass through our neighborhood regularly. Not frequently enough to be common, but often enough to be detectable with current technology. Every few years, if we're watching carefully, something arrives from beyond, carrying information about stellar systems we may never otherwise study. This is a new kind of space exploration. We can't send probes to other stars, not with current technology, not within human lifetimes. The distances are too vast, the energy requirements too extreme. But other stars are sending probes to us, not deliberately, but through the natural chaotic dynamics of planetary system evolution. Every few years, a comet or asteroid gets ejected from its home system, sent tumbling into interstellar space, and some tiny fraction of those objects eventually encounter our sun. These are sample return missions that we didn't have to launch. They're deep space probes that required no fuel, no guidance systems, no decades of engineering. They're gifts from the galaxy, arriving on their own, asking only that we notice them and study them before they depart forever. 3I Atlas will leave our solar system by the end of this year. It will pass beyond the orbit of Mars, then Jupiter, then Saturn and Neptune, and eventually Pluto, continuing outward until even our most powerful telescopes can no longer detect it. The sun's gravity will release it back into interstellar space, and it will resume its journey through the galaxy, perhaps eventually encountering another star system billions of years from now. But for these few months in 2025, it was ours to study. It was close enough to see, active enough to characterize, strange enough to captivate. And whether or not the spacecraft missions succeed in sampling its tail, whether or not we eventually explain all its anomalies, it has already accomplished something remarkable. It has shown us that the universe is far more creative than our theories anticipated. It has revealed that natural processes can produce results that seem designed, that seem engineered, simply because they emerge from conditions we've never encountered. It has demonstrated that our categories and classifications, our neat divisions between asteroids and comets, between active and dormant, between understood and mysterious, are provisional, temporary frameworks that reality will continually challenge. The nickel signature alone guarantees that 3I Atlas will be discussed and debated for years. Some researchers will focus on the exotic chemistry explanation, developing models of how nickel carbonyl might form in carbon-rich comets. Others will search for alternative explanations, exploring whether there are other ways to produce that specific elemental signature. And some, perhaps in quiet conversations away from official publications, will wonder whether we're missing something fundamental about what we're observing. This is healthy for science. Mystery drives research. Questions that lack easy answers force us to think more deeply, to challenge our assumptions, to develop better instruments and techniques. If 3I Atlas had been completely ordinary, matching all our predictions perfectly, it would have been interesting, but not transformative. The anomalies, the puzzles, the things that don't quite fit, these are what push the field forward. There's also a cultural dimension to these interstellar visitors that shouldn't be ignored. They capture public imagination in ways that many astronomical discoveries don't. People understand intuitively that something from another star system is special, even if they don't follow the technical details. It's a connection to the broader universe that feels tangible, real, almost personal. This engagement matters. It reminds people why we fund space exploration and astronomical research. It demonstrates that we live in an era of discovery, that the universe still holds surprises, that science isn't just refining old knowledge, but actively encountering new phenomena. When people read about 3I Atlas producing water at impossible distances or emitting industrial-grade nickel signatures, it sparks curiosity and wonder. And in an age where science sometimes struggles for public support, where research funding faces constant pressure, these moments of shared wonder have value beyond the scientific papers they generate. They remind us collectively that exploration and discovery are fundamental human drives, that understanding our universe is worth the investment of time and resources and attention. So what happens next? In the immediate term, we wait and watch. We hope that Europa Clipper's team finds a way to conduct observations during the tail crossing window. We anticipate JUICE's November observations. We monitor the ground-based telescopes as they track the comet's fading activity. Each new data release brings the possibility of another surprise, another anomaly that doesn't fit our models. In the longer term, we prepare for the next visitor. Because there will be one. The Vera Rubin Observatory, scheduled to begin full operations soon, will survey the entire visible sky every few nights, detecting objects far fainter and more distant than current surveys can find. When the next interstellar visitor arrives, we'll spot it earlier, track it longer, and have more time to coordinate observations. We're also developing rapid response mission concepts. The European Space Agency's Comet interceptor, scheduled for launch in the late 2020s, will wait in space at a gravitational stable point until an interesting comet is discovered, then quickly redirect to intercept it. If an interstellar object with the right trajectory appears during Comet Interceptor's operational lifetime, humanity might finally get a close-up view of material from another star system. Japan's space agency has proposed similar concepts. Private companies are exploring whether small, fast-response probes could be developed and launched quickly enough to reach interstellar visitors while they're still in the inner solar system. The technology is advancing rapidly, driven by miniaturization, improved propulsion, and most importantly, the knowledge that these targets are out there waiting to be studied. 3I Atlas won't be the last mystery from beyond our solar system. It's just the latest chapter in what's becoming an ongoing story of discovery and wonder. Each interstellar visitor brings new questions, new challenges to our understanding, new opportunities to learn about the incredible diversity of planetary systems scattered throughout the galaxy. And perhaps, just perhaps, one of these visitors will eventually provide answers that are stranger than we're currently prepared to imagine. Not because the universe is trying to deceive us, but because it's richer, more complex, and more full of possibilities than our current theories encompass. For now, 3I Atlas continues its journey outward, carrying its secrets into the darkness beyond our planets. We've learned some of those secrets. Others remain locked in data we haven't fully analyzed. And some, perhaps, will never be fully understood, at least not with current knowledge and technology. But that's the nature of exploration. Every answer spawns new questions. Every mystery solved reveals deeper mysteries waiting beyond. The comet came from another star, traveled for billions of years, passed through our small corner of space for a few brief months, and will soon disappear forever into the interstellar void. It was here. We saw it. We studied it. We wondered about it. The ghost comet came from another star, traveled for 10 billion years, passed through our small corner of space for a few brief months and will soon vanish forever into the interstellar void. It showed us hidden comas and impossible chemistry. It emitted refined nickel like a factory in space. It developed anti-tails that shouldn't exist. It revealed mysteries in perfect sequence, as if following some unknown protocol. Was it natural? Almost certainly. The universe is capable of extraordinary things when conditions align in ways we've never seen before. Exotic chemistry in carbon-rich environments. Ancient processes we don't understand. Physics we haven't discovered yet. But there's another possibility. One that careful scientists won't voice publicly, but that whispers in the data. What if some mysteries aren't meant to be solved immediately? What if some visitors are meant to make us question, to wonder, to realize how much we still don't know? We have the data. We have the observations. We have the facts. What we don't have yet are all the answers. And maybe that's the point. The universe, it seems, still has much to teach us. And 3i Atlas, with its industrial signatures and perfect timing and impossible behaviors, taught us the most important lesson of all. We're not as advanced as we think. The cosmos is stranger than we imagine. And the next visitor might be even stranger still. It's out there right now, fading into the darkness beyond our planets, carrying its secrets with it. Some secrets we've learned, others we've glimpsed, and some, perhaps, we were never meant to fully understand. Not yet.